correctly on the YouTube. Okay, so we don't like this picture because the machine tool is dirty. The vise handle is still on the vise on the YouTube, and I gotta now mute my. Okay, YouTube. So we don't like this picture because the machine tool is dirty. The vise handle is still on the vise. There. Now I have muted myself so we don't have to hear me talking twice every time. Could you guys hear it when it plays back again on my computer?
Yes.
Okay. If I do it just right, I could do like the row your boat and I could get a round going. Perhaps. Okay. I want to, so what is the fact? All right. So we don't like this picture because the machine tool is dirty. What does that have to do with stress strain and fixture design? The chips all over the place.
The chips could get in the way of the fixtures.
Chips get in the way of the fixtures. What else?
If a chip gets underneath the part in the vise, it could be kind of lopsided.
If you get it, if when you're putting your part in the fixture in the vise, if there's a chip underneath the part or underneath the vise or underneath the parallels, it'll make your part crooked when it comes out of the machine tool. It just in general, it's hard to work in that messy environment. When we're doing our machining operations, and if we're in, and if you've been in the lab,
Professor, your audio is looping and we can't hear whatever you're saying.
Is that better?
Yeah.
Yes.
That's much better.
Actually, how would you know if it's better if it takes a while for it to get bad? But all right, if you think it's better, then that's got to be better. All right, so see, some people thought my audio was just fine. Those are probably the people that weren't listening. Just kidding. All right, if on mute, it sounds all the same. So what is it that keeps the workpiece in the machine tool when we do these machining operations?
The forces that the vise exerts on the workpiece.
So if we're clamping the workpiece in a vise, the forces that the vise exert on the workpiece keep it in the workpiece. Now, I whenever I ask this question, I do it on quizzes all the time. I say, what keeps the workpiece from pulling up out of the vise? And invariably, somebody complains that they got the question marked wrong because they selected gravity. And so, yes, gravity does have a vector component down in this orientation. And gravity does help keep the part in the vise. And if the part weighs enough, if it has enough mass, all you need is gravity. But usually we don't have enough mass in our workpiece to fixture it with only gravity. And so if discounting gravity, if you assume that the cutting force is trying to pull the part up out of the vise, and that'll happen with the spiral flute on the end mill, as the cutting flutes engage in the material, they want to pull the part up out of the vise. What is it that keeps the part from flying up?
Clamping force.
So clamping force is important, but it's not the clamping force by itself that keeps the part from flying up.
Friction.
It's the friction between the workpiece and the vise jaws. Now, the friction depends on, what does friction depend on?
The two surfaces.
The normal.
It depends on the surfaces, the material that the surfaces are made out of, the condition of the surface, and the normal force, right? So the material and the condition of the surfaces make up the friction coefficient, mu. The normal force times the friction coefficient equals the amount of force that is achievable to keep the part from flying up in the fixture. Is that correct? I'm going to go with yes. That is correct. It's the normal force times the friction coefficient that results in the maximum amount of force that will keep the part from flying up out of the fixture.
How heavy of a part do you need to only rely on gravity? Like, it's got to be really dense, I would assume.
It depends. What does it depend on?
What you're doing in the
It
operation.
depends on the cutting force, right?
Yeah.
If the cutting force is really low, you don't need a lot of holding force or clamping force or friction force to keep the workpiece from flying out. Now, what's the danger of the workpiece flying out of the fixture?
It becomes a projectile going at a really fast speed through the air, and if it meets human flesh, bad things happen.
Yeah, one of the quiz questions that we're going to have is we talk about using a manual lathe, and a manual lathe that has a manual chuck key. If you've ever used a hand drill, and if you've ever installed a drill in the hand drill, you turn the little thing and it tightens down on the drill. And some of those drills, you have a little mechanical key that you can plug in. And when you turn that little mechanical key, you can get more clamping pressure on the drill bit, right? And so putting a drill bit in your hand drill, that's fixturing the drill bit in the chuck of the drill. So in a lathe, and in the lathes that you've used in the lab, we've used hydraulic pressure to open and close either a collet or the chuck jaws. And then it's the friction between those chuck jaws and the workpiece that keep the workpiece from rotating in the jaws and from pushing back into the chuck. So on some lathes, you have a chuck key like the drill does. And it's a piece of steel. It's maybe, 6, 8 inches tall. It's got a T handle on it that's maybe 6 inches across. And you interlock that in with the chuck and you turn that to tighten the chuck jaws down on your workpiece, just like you do with a drill. Now, if you start the spindle in the lathe without having removed the chuck key, the spindle might make one whole revolution before the chuck key comes out. And it's what is it? Centripetal acceleration that's going to make that chuck key want to go straight. Right. So one of your quiz questions is going to have you determine how much energy is in the chuck key when it strikes you in the forehead. Now,
is the correct answer too much?
Or enough, depending on your goal, right?
Yeah.
But I want you to actually mathematically show how much it is in the problem, and so I'm gonna now that I've set the stage there, I'm gonna play this video. This is not at WPI. It does look like it's a Haas machine, and it's a job shop. It's a machine shop, does precision machining, and they had a problem. Now, late in the video, he says, well, the machine's been acting up, and it certainly wasn't the program that was at fault. I'm going to guess that the machine did exactly what the operator told it to do at the moment the operator was talking to it, whether or not it was what the operator intended. And that's why I talked about software stuff at the beginning. But we'll play about 2 minutes of this video. We're going to see what happens. This is not from a lack of clamping force. This is from, well, he'll tell why he thinks it happened.
2019.
You guys can hear the audio?
Accident in the shop this morning where the spindle ran up to max RPM with a fly cutter in the spindle, and the fly cutter came apart. The counterweight on the end of the fly cutter looks like it broke the bolts. Is probably the first thing that happened, and then that caused an imbalance in the part or in the holder at 12,000 RPM and broke the pull set off. When that happened, the tool came out of the spindle, dropped down onto my table, and hit a curt vise. Thank God the operator's not injured. and everything went out the back, but it blew the Kurt vise clear off of the table, broke my tool setter, broke the jaws to the Kurt vise, threw the Kurt vise to the back of the machine and into the ball screw, weight covers. Pretty sure this is the counterweight that came out the back, and it went clear through the wall over to where another guy typically works on the other side. Luckily, he was not over there. That goes through that wall over to this side, through that wall, hit this chair, across the shop. So this is standing at this chair. Went across that shop. We were working over here on the other side of the forklift, where the guys are right now. Hit the concrete wall and went through that wall. It's a prime example of being extremely careful, guys. Not 100% sure what happened yet. We've had a good bit of problems with this.
So how much energy was in the counterweight when it left the machine tool?
A terrifying amount.
Enough. Yeah. So and I do this to stress that, you know, the walls on those machines are made out of steel. The doors are made out of laminated glass. Like the thing you look through is laminated glass, safety glass, and all that stuff. But we got to be careful, especially when you consider the amount of energy that is stored in the rotating thing that we're working with. So let's see if I can figure out. All right, so I'm going to close this. I'm going to close Facebook. Yeah, that was just a video that someone shared with me in a Facebook group that I'm in. All right, so now I'm going to stop sharing while I'm going through my whole thing here. All right. And I'm going to get up the presentation that I mean to use today. Present. All right, and now find Zoom again. There's Zoom, and turn the share back on. Screen share, desktop. All right, and so I think I'm screen sharing again. This is a picture of a different machine tool. You guys can see this?
Yes.
Yep.
This is a picture of a different machine tool. This is a WPI alum sent me this picture after he was setting it up. This is in a lathe. This was the workpiece, came out of the chuck due to excessive cutting force. Now the chuck is the fixture in the lathe, right? The workpiece came out of the chuck due to excessive cutting force. It actually hit the door, which you can't see in this picture, but it hit the door, bounced off the door, and then can openered out the back of the machine tool. So thank God the doors are thicker than the sheet metal on the back of the machine. That's probably not an accident, but I haven't talked to the guys that designed those yet. As an aside, I once sat next to a guy on an airplane who designs the shrouding that goes around the jet engines that one of the major jet engine manufacturers makes. So that shrouding is designed to contain the impeller blades in case the jet engine should come apart while at speed. His advice was don't sit next to the engines. So you can guard against these things. And what the sheet metal on the machine tool is doing is guarding, is trying to contain the energy of whatever might be flying around if something goes wrong. You can guard against these things, but you can't prevent them. So the guy that designs the shrouding on jet engines says don't sit next to the engine. So that's some advice you might want to heed when next time you get picking airplane seats.
Was it the Boeing one?
I'm not gonna say which jet engine manufacturer he worked for, but we were flying out of the airport in Hartford. So could have been one of two. All right, so fixture design.
Realistically speaking, could they ever make it thick enough to completely contain, or no, there's just too much force involved?
I don't,
Because I know those vices are extremely heavy duty and very thick.
oh yeah, one of those vices weighs 50 pounds.
Yeah.
Right.
So
And that slowed down the thing. Well, I guess the thing.
How many pounds did you say?
I don't know, like 50 pounds, 30. That's somewhere in that range. I haven't weighed one, but they're heavy. They made it. I mean, it's a big chunk of steel. Okay, so it's. I just wanted, again, this picture is just to emphasize that. It's friction between the workpiece and the vice jaws that tend to keep the part in the vice, right? So what happens when you don't have enough friction force? Well, one, you could throw stuff through the machine, but that's not normally what happens when you don't have enough friction force. Normally, you'll see something like this. Oh, this was a little cutting experiment that we were doing. So it was organic butter, 60 degrees. And so as the tool comes across, it makes the chip, right? You guys can do this at home if you want to see chip formation. So the cutting force in this is lined up in the direction of motion of the tool, right? So let's go to the next one. All right. Oh, I don't want to do that. How come the computer never knows what I want it to do? So here's what happens when you don't have enough friction and you try to do the same experiment. And so it's the coefficient of friction and the normal force that gives us our friction force, right? So in this situation, can we change the coefficient of friction? Right. The designer has chosen the materials we're going to use. So it's really hard for us to impact the coefficient of friction. And so when the tool comes in contact, the part moves, right? So insufficient clamping force is the problem, right? Because we can't change the coefficient of friction. So what happens when we clamp harder?
You're gonna smush the butter.
You can actually see we already broke it before we even touch it. If I had noted that during the experiment, I wouldn't have kept going.
would the solution be to like always have the cutting tool cutting into the front or back of the vise as opposed to laterally?
So I actually did solve it by creating a fixture that would also oppose the motion besides just friction. So that is roughly how I fixed the problem in order to do this experiment. But it's just it demonstrates, because typically we're not using, and this is a cutter that's similar to the one that flew apart in the other experiment, except here we're not spinning it. We have the spindle orientation locked. But this is the same style cutter as the one that can opener the other machine tool. So typically we're not cutting butter inside CNC machine tools. But when we cut things like plastics, we often actually, as a rule in the WPI manufacturing labs, if you tell us you want to machine plastics, we tell you no. Now, of course, that's not the final answer, but you have to convince us that it really needs to be plastic before we want you to machine it. Part of the problem is that we tend to make really small chips in plastic. Small chips get into the coolant system, they get past the filter in the coolant system, and they get jammed in the coolant nozzles, or they get jammed in the elbows, and you have to take the whole like sheet metal off the machine tool to clean out the coolant hoses. So that's one of the reasons we don't like plastic. But the other reason is because in order to get enough friction force, you have to clamp it so hard. And when you clamp stuff, so, all right, so you guys understand friction coefficients, right? And you know how to look up friction coefficients in reference manuals, or just Google it and say, what's the friction coefficient? What do you do if you can't find the friction coefficient for the thing you want the friction coefficient for?
you guess conservatively, or you use Google?
I was going to use science.
Oh,
You could do an experiment, but yeah, you could also just make a what do they call it? A swag, scientific wild ass guess, right? So you could guess conservatively. I like the conservative part, right? So we can look up friction coefficients. What we do in the lab is often aluminum on aluminum, or aluminum on steel, or steel on steel, steel on brass. Those kind of things. That's what we're normally doing when we do this fixturing. But when you get something like PTFE, when you get Teflon, stuff that's designed to not stick to anything, and then you try to machine it, what do you have to do to get enough friction to hold it in the machine tool?
change.
There's two things we want to do to get enough friction to hold it in the machine tool.
Can you use silicone or rubber?
I don't think that would help with PTFE, but yeah, you could use an adhesive, right? You could use something that it sticks to glue it to something. Pretty sure that wouldn't work with Teflon. It's really hard to glue Teflon to stuff. So what do we want to do? We want to, we need to increase our friction force by increasing normal force, because we can control normal force. We can control friction coefficient a little bit, right? If you change the surface of the vice jaws, you could clamp and you could plastically deform the plastic thing so that you get mechanical interlock between those vice jaws and the workpiece, right? What's the problem then?
You've ruined the workpiece.
Unless you can convince the designer to put that knurling pattern on the workpiece. Maybe you've done value added process when you did that, right? But so you could do a mechanical interlock. A lot of times you want to bolt the part down so that you actually use physical mechanical fasteners. But when you can't do that, all you can do is clamp harder or reduce the cutting force. We spent all last week talking about cutting force. What do we do if we want to reduce the cutting force? Two things we can change to reduce cutting force. I guess three things.
Lower the feed speed or the rotational speed.
Reduce. So reduce the feed rate.
Using a sharper tool.
Use a sharper tool.
Or depth of cut.
What about the
Reduce
approach
depth of
angle?
cut, right? So what you really want to do is you want to make the chip smaller. So reducing the feed rate or reducing the depth of cut, or reducing the feed rate, reducing the depth of cut will make the chip smaller. A sharper tool, especially in plastics, is a huge benefit. Plastics, wood materials, things like that want to have a sharp tool. Why don't you want to use a really sharp tool in steel?
Because it would just dull out.
It won't stay sharp very long. It'll get dull very fast. So it's better in a steel or in a hard material to actually grind a known radius on the cutting edge, so that it's not quite as sharp, but it stays consistent through the tool life. All right. So the more, back to present now. So the more we clamp something. Can you guys see all the little notices that pop up on my computer?
Yep.
Yeah.
Yeah. I meant to turn off all of the incoming notices to me, and I forgot to turn off the ones on my computer. All right, so when we clamp our part here, we increase the normal force, right? And our friction force equals normal force times mu. We can't control the mu because the designer controls that. What happens when you clamp something? What happens when you push on anything?
Newton's third law, an equal and opposite reaction.
So it pushes back on you with the same force unless we're accelerating. I agree. What if it's not accelerating? What if it's held fast and you're pushing on it? What happens to anything?
Deformation?
You deflect it, right? And it's either plastic or elastic deformation. So plastic deformation is when you change something and it stays the shape that you made it. Elastic deformation is when you push on something and then when you let go of it, it springs back. So like a spring, like a rubber band, like the table that you're sitting in front of, if you push on it, you're probably going to deform the tip of your finger a little bit, and you're going to deform the table a little bit. It'll be easier to notice the deformation in the tip of your finger because your finger is softer than the table, probably. Although those of you that haven't gotten out of bed yet, if you press on the mattress right next to where you're sitting, you'll notice that the mattress deforms more than your finger does, maybe. Depends. You get one of those memory foam mattresses. It's pretty cool. But so it deforms, right? It changes shape. And when you let go of it, it goes back to its normal shape unless you have plastically deformed it. We try not to plastically deform stuff when we're fixturing it in the machine tool. So we try to only elastically deform it. And so if we squeeze it and we machine a feature and then we let it relax, the feature changes shape. And so in this case, if we machine this pocket when we're clamping it, if we let go of it, then W1, the width number 1, is going to be bigger than the width original.
You have to take that into consideration when you're on Esprit.
You need to take it in consideration somewhere if you're using a material that's going to deform enough. So it's going to deflect enough so that when you let go of it, your part will no longer be in tolerance. Right? And so I'm presenting this a little bit out of order. So you can take an entire class on stress and strain here at WPI. I believe the title of the class is Stress and Strain. Or stress analysis, maybe, stress analysis. Has anybody taken stress analysis?
Yes.
Yep, you have. And so what do you spend all of the other days doing? Because this is the formula, right?
We just do a lot of examples.
And they all come back to this equation or this set of equations?
Pretty much. There's a bunch of more complicated stuff, but this is like the fundamentals of it.
Exactly. So stress is force over area. Now, I do want to take a step back. Has anybody had any mental stress this year? I'm going to just go with yes. We've all had some mental stress this year, right? What causes our mental stress? Is it things pushing on us? Things from outside pushing on us? Mental stress usually comes from outside. Or if it's from inside, it's because of things we're thinking about might happen outside. So mental stress is coming at us. Our stress is coming at us. It pushes on us. We've only got so much area in ourselves, right? And as that stress impacts us, we feel strain. So when we talk about stress and strain in mental health, it's exactly the same as engineering stress and strain, except it's easier to do the math in engineering stress and strain because it's easier, one, to measure the area. I know from experience that eating more does increase the cross-sectional area, but it does not actually fix the strain problem. Okay. But strain is the change in length or the change in dimension that happens because of the stress. If you plot stress versus strain, you can get an elastic modulus. That elastic modulus is a bulk property of the material. So different materials have different elastic modulus. If you know the elastic modulus and you know the area and the force, you can figure out the strain. If you measure the strain by measuring the change, and you know the force in the area, you can figure out the elastic modulus, right? Okay, so if we come back to this slide, you should be able to figure out the change in dimension, that change in width, based on knowing the clamping force and the elastic modulus of the material. How do you find out elastic modulus?
Look it up.
Look it up. So one of the things that that people say about engineers, and I don't believe that it's entirely true, but it has merit, right? Pretty much all stereotypes are based in something that has merit, right? It's usually taken out of context, and it's usually well displaced from the group as a whole. But they say that engineers don't need to know anything. They just need to know which book to look in. I would say that if you don't have a fundamental grasp of the physics, you'll never figure out if there's a book that has the thing you're looking for. But I also think that that's why companies that are hiring engineers always want somebody with at least 5 years experience, because they want the previous employer to have purchased all the books for you. So they don't want to have to buy the books for you. So knowing that we can calculate this, and we can look up what's the elastic modulus, we can look up what's the friction coefficient. If I told you the material properties, so if I told you the material that we're cutting, and I told you the feed speed and depth of cut, could you estimate the power?
Yes.
So if you knew the material and the feed speed depth of cut, you could estimate the power. If you know the power and you know the feed speed depth of cut, could you estimate the cutting force?
Yeah.
You won't necessarily know the direction, but you'll know the maximum magnitude of the cutting force, right?
Like not including like if it's like a bit that's rotating.
Well, that's why you won't necessarily know the direction, because the direction of the cutting force is going to change as the tool rotates.
Okay.
But at some point during that rotation, all of the cutting force will be in a direction that's bad, that wants to make the part slide sideways in the vise or pull up out of the vise, right? So if you're doing an estimate like this, and when we're modeling these things, what we want to do is we want to do like a worst case estimate, right? At the beginning, Sam wanted to be conservative when he guessed what the friction coefficient was. Was it friction? I think it was friction coefficient.
Yeah.
Right? So we want to be conservative. So let's assume that all of the cutting force that we can apply, because we know what the estimated power is in a direction that's trying to pull the workpiece out of the fixture. If we make that assumption, then we can say, all right, so I know if I have this material and I have this much feed speed and depth of cut, I can possibly have this much cutting force. Therefore, I must have that much clamping force to keep the part from moving. Is that a reasonable assumption? And if you have that much clamping force and you know what the elastic modulus is, you can tell how much elastic deformation is the part going to have before you start cutting. So we can use what we've learned in all the other modeling things to figure out, all right, so is the part going to move? Which is why it's way simpler for the lab staff to say, no, you can't cut plastic in these machines. Then we don't have to help you figure it out. But in reality, we do cut plastic in the machines. We just try to control when and where we do it. What's the easiest way to not have so much deflection that you can't make the part the shape you want?
Bolt it down so you don't need to use as much clamping force.
Okay, so we could find a different fixturing method. If all we cared about was this pocket, we could put 4 holes in the workpiece first, and we could bolt it down to a plate. In our machining company, one of the things we do is we machine ceramics. So it's hard to clamp on ceramics. If you clamp too hard, they shatter. So they don't deform as much, they shatter. On the other hand, super glue sticks really well to ceramics. So one of the things we often do is we use super glue and we glue the ceramic part to a piece of steel, and then we hold the piece of steel on a magnetic chuck. So you could use magnetism to hold something that's steel, right? You just need force. You need a normal force to provide frictional force. You can also locate things up against a jaw. So somebody said with the butter example, why don't you cut the other direction, right? And so we could put a stopper in that vise so that whatever cutting force we're pushing on the butter with pushes it against the stopper, right? So we can add to the frictional force with other mechanical features. But in general, we're using this frictional force to keep the part in the machine tool because it's the fastest and easiest way to do that. All right, so when else are we going to have to worry about elastic deformation besides clamping?
Like if you're using a like very elastic material on the lathe, like a plastic, when it spins really fast, it could expand.
Ooh, yeah. Or if it's any little bit off center, it will just bend. The tiniest bit off center will make it unbalanced when it spins, and it will just bend. In fact, if you go into the lab right next to lathe 1, there's one of those wooden posts, the columns that hold the building up, and you'll see one of them has a big divot out of it. That's because somebody was too lazy to cut their stock material to the right length to fit it in the lathe, and they stuck a long piece of stock material into one of the lathes and clamped it at the cutting end, and then started the spindle. And as soon as the piece that was sticking out the back of the lathe started going around unsupported, it bent. It was the stock material was 1-inch diameter aluminum, so you can imagine just bending that over your knee. It made about 10 rotations, taking a chunk out of the post each time it went around before the person managed to hit the e-stop. He said, you guys know if you break something in the lab, we want you to write us an email to ibrokethis@wpi.edu. We want you to tell us what happened, what you were doing, what happened, what's the approximate expense to WPI, what's the cost to WPI for your mistake, and what would you do next time to make it not happen again. And so when he wrote his email, he said, as soon as I realized what the whump whump noise was, I hit the e-stop. So it had to have hit the post at least twice, but I think I wasn't there in the room when it happened, but I understand it was about 10 rotations before he hit the e-stop and stopped it. So yeah, you have to worry about deflection of your part. Usually it's not just caused by the rotation. Usually we've got the part sticking out of our vise and we're pushing on it with a cutting force and it deflects. Now, if we push on our part with a cutting force and it deflects, are the two edges going to be parallel? Let me get the screen share off for a second. If I can find the button. Stop screen share. And I want to turn on the other camera. Come on. And now you see the whiteboard. Okay. So if I've got my lathe chuck here, and I've got my workpiece sticking out of the lathe chuck here, I'm supporting it here, and I'm going to do a turning operation. I'm going to feed in this direction. And my tool path, let's see, I'm going to come down here. And my tool path is going to be like this. And so we're assuming that I'm intending to take a constant depth of cut off the part as it comes around. And so the finished part, I'd like it, You can see that I'm an engineer, not an artist. But I'd like that part to be smaller diameter by feeding across like that. Now, as soon as the tool touches the workpiece, there's going to be a cutting force in this direction, right? There's going to be a force this way that's causing that workpiece to deflect. What's the finished shape of the workpiece going to be? It's either going to be something like this, or something like this. Can't really see the blue, can you? Try brown, try green. So is it going to end up as the green part or the orange part?
Orange.
Anybody say it's going to look like the green part?
Yeah, I'm thinking the green.
It's gonna, yeah, like the green one.
You think it's going to look like the green part? So let's do a quick poll with the in the thing. Raise your hand if you think it's going to look like the green part. You got to do it quick because the hands go away. Really, only 10 of you? I see they go away too fast. I don't like this. I liked it better when they stayed until people turned them off. All right, so a bunch of you think it's going to look like the green part. Let's think about it. As the piece deflects, it's going to go like this. Because of the cutting force, right? But the tool is going to still go like this. And so when it comes back, after we don't have a cutting force, it's actually going to be wider at this end and narrower at this end because we're supporting at that end. You can calculate how much. If you know the elastic modulus, well, you can calculate how much it's going to deflect if you know the elastic modulus, that's E. If you know P, that's the force, so that's our cutting force. If you know length, L, that's the distance from the support out here. L is the distance from the support. So L changes as we feed across the workpiece, right? The closer we get to the support, the shorter L is. And you have to know I. What's I?
Inertia.
So it's the area moment of inertia of the workpiece. The area moment of inertia depends on the shape of the workpiece. Since it's a lathe, we're going to assume that it's round. If we assume that it's round, I equals pi r to r cubed, or r to the fourth rather, divided by 4. So the radius of the workpiece, the diameter of the workpiece, is taken to the 4th power, and the length is taken to the 3rd power. So what we really want are short, stubby workpieces. They won't deflect very much. Long, skinny workpieces will deflect a lot. Can you compensate if you know how much it's going to deflect?
Yes.
Could you have the
In
tool
theory.
not move in as much in theory, but it probably wouldn't necessarily work?
So, well, you can reduce the cutting force by reducing the depth of cut and the feed. You can hold the part closer to the point where you're cutting. So you could incrementally move the part out if you had a long cut to make. you could remove material in a different way. I recently actually had to do this. Let me switch cameras, turn off the screen share. So I recently had to take a fairly long workpiece. So it was 3/4 of an inch in length. I needed to cut 1.5 inches of it. So we're supporting it over here. And I needed to make 1.5 inches of it be about 20 thou in diameter. Have it be the same diameter all the way out. And then I had to have a big section out here. Now, my instinct would have been to take a piece that was already 20 thou in diameter, drill a hole here and stick it in. But I didn't have time. Oh, sorry, this is not 20, this is 200 thou. It's actually, it was about 115, but whatever. Doesn't matter. Doesn't matter what the final dimensions are. So if I had a tool path that came across like this, by the time I got about that thick, there was too much instability out at this end of the part, and the part would bend and come around and hit the tool and break. So I couldn't cut it that way. What is my other option?
Isn't there a way to secure it from both ends?
You could secure it from both ends. And there's a way, we have a lathe with a tailstock, and basically it's a little thing that comes in at the other end, and you push that way with a little point. You've drilled a hole in the end of this thing, and now you've supported it at both ends. Unfortunately, because of COVID, and because we didn't use the tailstock for a long time, the tailstock doesn't move in that lathe right now, and we haven't yet had a chance to fix it. So I didn't have that option available to me. There's actually an option where you have something called a, the word escapes me, but you can have a piece that follows the tool across. That's got a roller on here, and so the tool's on this side. The thing with the roller supports opposite the tool also. But we don't have one of those available. So what can I do by changing the tool path to possibly make this work?
Put it in increments.
Yeah, what I did was, instead of coming straight across like this for each pass, I went like this. And so everywhere where the tool was coming in contact, it had a piece that was 3/4 of an inch in diameter to support, and it just had a little bit here that I was removing material as the tool came in. And so I was able to make that part without any special fixturing, just by adjusting the tool path and adjusting when I was applying the cutting force. So you can do simple things like that. All right, so we got our cantilevered beam, deflection, we've got our squishy stuff. I think that's it. It's perfect timing. I only went 5 minutes over, which wouldn't have happened if I had given you guys the correct link for today's lecture instead of the link for next Monday's lecture. I'll fix that. I'll fix it for tomorrow.